All right, so we're back at the shop, and the shop is clean. We are ready. We're ready to start laying up parts. So this took way longer than you'd ever expect it to take, but pretty happy with it now. We're gonna put skirts. These are just muslin. We're gonna put skirts on everything so that we don't cover it in dust again. But we're ready to start actually making parts. And first thing we're gonna do is make templates. So these are the molds. So this part right here, that's sitting over there on the bench. We're going to repair this. I made a molding error about 5 years ago, and I'm going to correct that today, and then I'm going to reject these 4 parts, sadly. There's a molding error of about 3/8 of an inch right here, and it's in here. One of these is correct, one of these is short. So what I'm going to do, this return that creates this flange, all I have to do is move that out 3/8 of an inch. I'll backfill this with flocks, let it cure, and then it should make the correct part. I feel like I can take 1 pound or 2 out of each one of these, and you know, that could save 5 pounds on this whole deal, 5 to 6 pounds. The rest of these I'm happy with. These are good. These are the covers. What has to happen is that I've got to put together a fixture to bond all this up. This ring here, this is where the fan, this is the fan casing really, and then this is the inner duct wall, and it has an ogive sort of profile in here that interacts with this. This is the cone shape. These two things interact with each other to create either a divergent duct, a constant area duct, or a divergent duct. This translates in and out. Okay, this feature here this creates a cavity. The linear actuator lives in this cavity. And these features right here, these accept the bearings. Okay, and they're just going to be bushings really. And then the central shaft, it slides on the central shaft that is also the idler shaft for the fan itself. And so this slides back and forth and creates and varies the exhaust outlet from convergent to divergent. All right.
Is that a form of trim for the motor, or for the velocity? Or
yeah, it trims the velocity of the air coming out of the fan system, so that it creates a correct amount of thrust for a given power level at a given altitude.
Different than having to use a throttle for more than less.
Think of it as a constantly variable propeller. Okay, it's like a constant speed prop. Not quite as effective as a constant speed prop. We're going to find out how effective it is, but it'll allow the exhaust gas velocity to match the free stream velocity outside the airplane times its whatever our propulsive efficiency is. In other words, it'll allow the efficiency factor of the propulsion system to be wider, the area of efficiency to be wide enough so that it doesn't just hit its design parameter and really not do anything else. It has to operate from 0 airspeed up to 300-ish knots, so I have to have something. Anyway, this is what I'm going to do. We'll test it and we'll see how well it works. So I'm going to remake that.
How are you going to test it?
Well,
just see what kind of thrust it is. How are you going to do that?
Well, we're going to put the propulsion system together.
Okay.
So starting to get our crap together here. We've got all the turbo stuff. This is more of the turbo stuff. These are the flanges and things that I had made to build out the turbo manifold. And this came in. This is the shaft. And this is a custom length C5 Corvette shaft. So this interfaces with the Gubios, as I've explained in a couple of other videos. These go on here, and these came in as well. Here, had a couple of these made. These are the interface plates. This bolts onto the to the flex plate on the end of the crankshaft. We'll put spacers onto here, and then this becomes the interface with the Gubio. And then there'll be a pilot shaft that goes into the 20 millimeter bore in the engine, keep everything running concentric. And we pick up the 4 holes on the outside of the stock flex plate drive. And then these also came in. And these are the engine mounts. I had 2 of them made. And they bolt in between the block and the oil pan.
Is that the one you showed you had a cardboard make out of it, or
I was prototyping it, and I printed it out. I cut one out of wood. We test fit it. I did that here and here.
And that's the finished product.
This is the finished product. We're probably gonna.
That's nice work.
Yeah, they do a good job. Okay, this is a send, cut, send, and this is these are laser cut. Yeah. We will probably polish them out. We'll take the holes out a little bit bigger, and drill them so that we don't have these rough edges. There's a possibility of these rough edges creating a stress razor. So we'll polish everything, right? But in general, pretty good and reasonable, right? So we got all this together, pretty happy with it. We can finally move on. So the objective is, I ordered the 3D printed manifold. Should be arriving at Dad's house today sometime. It looks good. And I ordered it from Xometry, and I had them make it on a laser sintering machine. So it's nylon 12, should be coming in. We'll drill it, we'll tap it, we'll seal it, and we'll put it on. So in principle, we have almost everything we need to finish the engine installation, including this. Fuel Tech is also an engine monitor, and it has a bunch of inputs and outputs that will allow me to run a bunch of the administrative tasks of the airplane. For instance, I can run and monitor things like flaps, trim. There's enough I/O in here to do that. That's a very, very nice little unit. And I read up on it. I printed everything out, and I think it's going to do really well for me.
How expensive is it?
All of this, and it includes the wire harness, two of them, and an O2 sensor, and some pressure sensors, and the wideband O2. Okay, so this is a wideband O2 controller, and all of this was about $2,500 bucks.
It's not bad, really.
For the value, no, it's really not. For the value, it's going to do a lot for me. It satisfies a bunch of requirements. It's a very elegant solution to what could be a clusterfuck of a problem. So we'll run these. We'll run all this probably straight to the firewall. and we'll probably interface with a 38999 Canon plug at the firewall, and then we'll plug from the airplane or from the engine compartment to the firewall with the 38999 Canon. Probably 32 pins, maybe 2 of them, but I have to check how many pins. This is about 38 pins. So the pins, I need that many pins. Now this is a fairly simple system. Fundamentally, to keep the engine running is not, it's this sensor, it's the throttle position sensor, it's manifold absolute pressure, and it's manifold absolute temperature, and then crank position. There's really not that many inputs and outputs to keep the engine running. If I want to later, they make a version of this that doesn't have the screen, and it has the same form factor. So I could use that as a backup. All right, so you can just put that one on the back side of that. All of this will go into the engine instrument pod, and Bob's your uncle. So yeah, this is most of the engine. Well, this is almost all of the engine management right here. So it's a matter of, and the engine installation, I need to have the exhaust manifold welded up. I'm probably gonna tack it together. We have a good welder in the back. I need to get my welding chops back, but what I'll probably do is simply tack everything together, hand it off to somebody, and have them purge weld it all together, and it comes back. But all the pieces are here to do that with. This is how I do a quick and dirty template. These templates are the cutting templates for the material for the fan system. And this is just something that developed over the years. It's efficient, it's cheap, and once you get, it's a good way of prototyping a template, a cutting template. I just take this butcher paper and we do a first cut, and then once I'm happy with it, we just line it with just tape, and then we'll keep some notes here. Right. For instance, this is a cutting template for the foam on this. Here, I'll go grab it. Go ahead and just stay there, Dad. So this is the foam, this part here, and this part is here. And the notes are, this is PFA 5, this is my part number. My part numbering system is, it's a dot delineated part numbering system. I have a 3-letter designator up front, point, and then a numeral after that, point 1, point 0, point 0. That allows it to stack up nicely in a spreadsheet, and it tells you where in the indented bill of materials you are. Every point is 1 level down in the bill of materials. Anyway, that's just how I do it. Everybody does it a different way. So I start with the part number. If I don't have part numbers, this is what it is. This is the centerpiece of whatever. Okay. And then what is it? Divinycell foam. And this is 1/4 inch Divinycell and scrim down. Okay, scrim down and scrim up. It's nice to be able to find stuff in a shop. Okay, this is scored Divinycell foam. Well, it's a PVC foam. This particular stuff is straight up Divinycell. I bought a bunch of this other 3-pound foam, 2.5 to 3-pound foam from a marine supplier. It's a very common marine grade material.
Is that thick enough to do anything? I mean,
it's right here. You bet.
but that's thick enough to hold, huh?
Yeah. Okay, this is 1 ply of 3K plus or minus 45 degrees. Actually, this is plus or minus 0 core, and 1 ply. Okay, you can't dent this. This is really extraordinarily good way to build a part. I can't make this much lighter. Right, it has some extra material on the edges to stiffen up the edges where we're going to do a mechanical interface. But in general, this is about 3 pounds. I might be able to shave a half a pound, right? So yes, the whole concept of having a core is kind of magical. It brings the skins apart and increases their cross-sectional moment. That's what it does. It takes that material, moves it away from the center axis, increases its cross-sectional moment of inertia. And that's how it works. And it has a magical effect on strength, or specifically stiffness, secondarily strength, but mostly stiffness. So this is what makes that gap. You can do foam, you can do end grain balsa, you can do honeycomb. All right, for this project, with this method of building and doing wet laminations, you want something that will control the resin inside the core. You don't want it just filling the core. Okay, we couldn't do this process very easily with a hollow core, right? Something like a honeycomb. That works with prepregs. We can make our own prepregs and then lay this up. It does work, but you're going to get a lot of weakening of the wet material down into the cells, and you stand a chance of filling the cells. But this will control all of that, and it will allow enough resin to come up through these gaps to create a really stiff core. And it'll also allow the air to transfer up from what is the laminations that are against the mold surface up through the core, through the inner layer, into the bag material. Okay, I'm not going to go too deep into bagging technique until we just do it, you know. But this is basically how I make a template, and there are notes. 45 degrees. This means I'm beveling 45 degrees. The scrim part of this is down, right? This part is the scrim. This holds all of these squares together. And sometimes if you have a part that is there's too much curvature, then you might want to split these. You just run a razor down these and you split them so that they conform a little better. The reason I did scrim down on this is I was trying to control on that mold. I did scrim down because it's a convex mold, right? And it just lays down a lot nicer, right? So when you prep this material, it's just like any other flat material. You might have to, you've got to look at the topology of your part and decide where you're going to make cuts, right? This is going to have a hell of a time going around this ogive curve here, right? So when I did this, I just stopped it at the ogive. All right, so this part is a 1/4 inch core, and this part is just homogeneous carbon fiber, and I believe this is 6 plies. But I'd have to go look. And then I created a flange here, and then I created a flange that goes all the way around. Now the only way to do that, you can come in here, Dad. The only way to do that is to make parts that come off your base mold. Right, so these parts are called addendums. Right, and they create returns and features in the mold that if you kept them on here and they weren't removable, you wouldn't get the part out. So to create all of this feature in one part, I had to have a relatively complex mold. A complex mold creates a simple part. It's that. That's a good way to put it. The more complex the mold, the simpler the part. If you can remove secondary operations in your tooling process, your better off taking the time and tooling. I call it tooling deep, right? You could just make this part and make it a single draft part and it'd come up, and then I've got secondary operations and what have you, right? But if I can get most of that stuff into the tooling, it's completely controlled. For better or worse, it's completely controlled, and it's completely repeatable, and you have eliminated secondary operations, and that's how you go fast in assembly, right? You can go fast in layup and then slow down in assembly because you have a lot of handwork to do. I'm trying to eliminate most of that handwork in assembly, right? Okay, so back to template making. These are all of the templates, and I just use this as a document. So these are the courses of material, and these are the notes that I've taken. This is 3K45 ply 1, uni. So this is basically the lamination sequence, and it's a good way to just, okay, I need this many, and this is the orientation, and this is the size, and this is the material. This is a good way of doing it. Okay. Now we're going to do this one. This is one of the last pieces of that puzzle. And this is just like haberdashery. This is just like dressmaking. You're going to take this flat thing, push it in here, and get a document of this shape so that you know how much material you need to come up over the top and over the flange. And then I'm just going to mark it. And I know that this, I have, let me look at my lamination. All right, so these are my notes from the making of the casing parts. I blew a lot of parts getting this right. What I eventually came up with was I had to prep everything, including the bleeder and the release ply, ahead of time. And it's this is what I came up with, and I was able to get effective, repeatable parts. But this is a difficult part, and it doesn't really show right there. But you shouldn't be able to make this part with the way I'm doing it. But I got away with it. We'll go a little bit deeper into this, but this is kind of what it takes. These are the notes I took on the floor, right, as I was developing a process for doing this. Now these are the parts in question, and then these are hand-drawn laminations that I eventually ended up doing. Sometimes it's easier for me just to do it by hand, and then I'll go back to the CAD. Sometimes I like to start in the CAD, but a lot of times what you have in the CAD doesn't cut it. Okay, so you get it out there, but at least you got something. You got something to start with. Then you start redlining the crap out of it. All right, but this is how I had to structure the workflow in order to get these parts to do what I wanted them to do. And they're good, except that I have a molding mistake here at the end of this flange. And this is what would be called a process instruction, MPI. A bunch of different acronyms for it, but basically these are the instructions. And the way we used to do it, which makes a lot of sense, is that you have a definition of part up front, and then you go ply by bloody ply. All right, just one. Okay, this is where we are. This one is marked out. One at a time. This is our first one. Second, are we done? Yes, turn the page. This works pretty well. So this is the part in question. Pretty simple part. This is 3K plus minus 45, alternating 90s and 45s out to, this is 30 plies, 35 plies. This is taking all of the structural load of the fan. And so this is really beefy, and it's going to be it's coming all the way out to just under 1/4 of an inch. The base itself is 0.375 of an inch, so I will have a core in here of it'll be a high density core. In other words, it's just going to be like scrap carbon. All right, and then I have the exterior and interior laminations that come up along the flange. So here's the flange. I'll have like a 3/8 of an inch build on this plate, and just under 1/4 inch of a build all the way out to here. This will get vacuum bagged. It will get, we're going to just throw this in a turkey bag. And you can get away with all of this because you just throw the whole thing in a bag. All right, I'm not trying to seal against here and then worrying about this seal. No, this whole thing goes in a bag. You know what works really well? These are really good small.
Regular 42-gallon
These are the contractor bags. The nice thing about it, if you're not going to a lot of heat, these won't take any heat. But if you're going to go to 100 degrees, 120 degrees, just to get a nice cure, this works beautifully. You just throw this in, you seal this up, and it will conform to everything, and it stretches a lot before it goes off. Now, we have the right shit. We got the good shit. At great cost, we have the good shit. And for the big parts, we will use it. We've got this is a bag film. I got like 50 yards of bag film. No, I've got 100 yards of bag film. But for small parts, this is just a happy accident. So I tried this one day, and I'm like, holy crap, that works really well. So, you know, cheat code. Black plastic bag, okay? Cheat code. Quick and dirty template. Make your notes on it.
Perfect.
Okay?
Okay.
All right. That's about enough for today, don't you think, Dad?
I think it's good. It looks good. The shop looks great. Everything looks good, son. I'm real proud of it. It's all really nicely done and ready to go.
Thanks, Dad. We're gonna start making parts here. It's about time.
I'm going to see an airplane in here for you.
Yeah. We're hopefully in a couple of months.
The tires are here, everything.
Yeah, all the systems have been working in the background, and I'm hoping to have everything starting to come together this summer.
Yeah, it's great.
All right.
Appreciate
Till next time.
Good. Thanks.